half-life, rate of radioactive decay basically just depends on how much radioactive sample is present. When we say rate essentially in chemistry means speed. So if we say rate of radioactive decay, that we are simply talking about what is the speed at which the radioactive sample is disintegrating or it is decaying. It is also called as activity of the sample. It always follows a first order kinetics. So we'll talk about first order kinetics when we get into chapter kinetics. So if you are interested in learning more about this, you can look into chapter chemical kinetics. But for now, just remember radioactive decay always follows a first order kinetics, which essentially means that the speed at which a radioactive decay occurs is directly proportional to the number of nuclei present, which means that if there's more atoms or more nucleus present, that means the speed of reaction would also be equally high. So that's given by this. A is the speed of the reaction, which is also called as the rate of the reaction. N is the number of nuclei that are present, which essentially is same as the number of atoms. Each atom has one nucleus. And K here is called the constant. It's specifically called as the rate constant or the decay constant. Rate constant simply means it's a constant for the rate of a reaction, for speed of a reaction. Decay constant because this here we are specifically talking about radioactive decay. So the larger the value of K, the higher would be the activity of the substance, and the greater is the number N, similarly greater would be the activity of the substance. So this is one way of representing first order kinetics. This is an integrated rate law that is used to express first order kinetics, any first order kinetics reaction including radioactive decay. Here N0 is the initial isotope atoms that are present, initial number, original isotope atoms number that is present. N is the number of atoms that are remaining after time t has elapsed, and t here is the time. T half is called the half-life of the sample. So this is an integrated rate law. If I'm ever interested in figuring out what is how much amount of sample is left, of a radioactive sample is left after, let's say, 2 minutes, I need to know what is the initial sample. It would, if I can calculate N from here, I can calculate how much sample is actually left after time t has passed. ln2 basically just is a mathematical term, natural log of 2. T half is the half-life. Half-life simply means that if you take a sample, the time that it takes for half of this original sample to disintegrate is called the half-life of the particular sample. So every half-life, half of the sample is dissociated or disintegrated or decayed. So the number of nuclei remaining is halved after each half-life. So if, for example, if I start with 100 samples, 100 nuclei, after one half-life, one t half. So t half basically just stands for half-life. After one t half, I would have half of it left, which is 50. After the second t half, I would have another half left. Half this time of the original. Original now is 50. So I would have 25 left. After one more half-life, I would have 12.5. After another half-life, that would be half of the 12.5, which is 6.25, so on and so forth. This basically means this half-life for a first order kinetics or a radioactive decay is fixed. So if this is 10 minutes, in 10 minutes my sample would become 50. In another 10 minutes it would become 25. In another 10 minutes it would be 12.5. In another 10 minutes it would be 6.25. Okay, so you can see that in the first half-life, almost how many atoms disintegrated? 50 atoms disintegrated. But when I look at the second half-life, it's the same amount of time, it's still 10 minutes, but how much sample has disintegrated? It went from 50 to 25, so only 25 atoms disintegrated. In the third half-life, the sample started from 25 and became 12.5, so in the same 10 minutes, only 12.5 atoms this time disintegrated. So with time, we can see that the number of atoms that are disintegrating or decaying is becoming lesser and lesser, and that basically is first order kinetics, that as time passes, the speed of the reaction will keep on reducing because your starting material is reducing in its amount. That is called first order kinetics. But the t half is fixed. 10 minutes, 10 minutes, 10 minutes. The half-life will always be 10 minutes. So it would take 10 minutes for your sample to become half if you start with 100 samples or if you're starting with just one sample. It does not matter. The t half is fixed. And the value of t half can be calculated using this formula. T half is ln2 over k. K is again the rate constant or the decay constant, whatever we want to call it. It's a constant term. So if I know k, I can calculate t half using natural log of 2 divided by k. If I know t half, I can calculate k, rearranging the equation. This equation will be provided to you, and also the previous equation that we showed will be provided to you if a question is asked, so you do not have to memorize it. One good way, a lot of times you'll see some easy questions from here. For example, if I'm starting with like 100 nuclei, how much or how many nuclei will be left after, let's say, 4 half-lives? After 4 half-lives, how much sample will be left? So you can either do this one step at a time. 100 will become 50, that's 1 half-life. Then it would become 25. Then it would become 12.5, that's third half-life. Then after fourth half-life, we would have 6.25 left. So how much is left? 6.25. Or there's an easier formula for this. How much fraction is left after n half-lives is 1 over 2 to the power n, because after each half-life, it's 1 half, right? So if you take 100 times 1 over 2 to the power 4 half-lives, that's 100 times 1 over 2 to 4, 16, which would also give you 6.25. So either way, you can calculate this, whichever way works for you, the longer route or the shorter route. Okay, so now we'll look at lot of examples based on these two equations that we saw. One is half-life, another one was integrated rate law. Calculate the time required for 60 gram sample of C14 to be reduced to only 7.5 grams. Half-life is 5730. So how much time is needed for this? Okay, so as long as these two numbers are multiple of each other, 6.60 and 7.5, it's pretty straightforward. In the first half-life, 60 would become 30. Second half-life, this would become 15. It would become half of 30. Then the third half-life, 15 would become half, which is 7.50. So it has undergone 1, 2, and 3 half-lives, and that basically means it's 3 times t half, which is 3 times 5730 years, and that's your answer. That's how long it would take. If 43.2 milligrams of certain radioactive isotope disintegrates to 10.8 milligrams in 59.6 seconds, what is the half-life? So the question is asking what is the half-life. Now there are a couple ways to do this. If you can think in your head that these two are multiples of each other, in a factor of 2, then that's great. That makes your life easier. For example, 43.2 milligrams. If I take 43.2 milligrams, this was my initial sample. Now it is 10.8 milligrams. If you divide these, you will find that the ratio comes out to be a ratio of 4, which means it has become 1/4 of the previous sample. Initially it was this, now it is this. So it has been reduced by 1/4. Which means in 1 half-life, it became, in 1 half-life, it started from something and it became half. In the second half-life, it became 1/4. So that's what this is. If this is difficult, so you can say 10.8 divided by 43.2. That's also 1/4, which means my sample has gone 1/4, which means it has gone through the half-life 2 times, which means total time is 59.6 seconds, which means one half-life is going to be half of 59.6 seconds. So that's your answer. Take half of this. Or if this is a little bit tricky, we can also use the integrated rate law that we saw earlier. Integrated rate law is this is the integrated rate law. You do not have to know if these are multiples of each other or not. So the simple concept is, if 43.2 milligrams of radioactive isotope disintegrates to this, which means this was initial sample, so initial means it's N0. This is the final sample after time t, so this is my final sample. This is how much time has passed, so this is t. You just have to plug all these values in here. So natural log 43.2 milligrams divided by 10.8 milligrams, just remember you want to use the same unit, equals natural log of 2 divided by t half, everything multiplied by t, which is 59.6 seconds. So if we try and solve for this, from here if I try and solve for t half, I would get the same answer. You just have to rearrange this equation. It would still give you the same answer as what we saw before. So you can even use this approach. That's just a formula that you need to use. It can also give you the exact same information that we were able to get from the half-lives. Okay, let's try different types of questions that you can get from here. Calculate the time it takes for 6.75 times 10 raised to power 18 atoms of an isotope to disintegrate to a point where 8.9 times 10 raised to power 17 atoms of isotope remain. The half-life is given to you. So half-life means t half is given. This is how much sample that was present before. So this is N0. This is how much sample is left after some time has passed. So this is N. The question is asking how much time it took. So again, we will use the same equation, which is the integrated rate law. So if we'll take our integrated rate law, plug in all our values, N0, N, t half, and natural log, and from there you can find what is the value of t. So here we have just rearranged the same equation. You're just plugging all the values in, rearranging the equation, and solving for t. I could ask you any type of question using the same equation. The equation is same. There's only one equation that you have to use. I can ask you to what is N0 and give you everything else. I can ask for N, give you everything else. T half can be given, can be asked for, everything else would be given, or T will be asked like in this question and everything else will be given. So the question stays, the equation stays the same. You just have to know what is the question asking. There are more examples that you can try on your own as well. For example, a particular isotope has half-life of this. So this is the half-life. How many atoms of this isotope remain after a sample containing these many items is left for this much time? So this is T. A sample containing these many samples. So this is my initial. Question is asking how many atoms will remain, which means it's asking what is happening finally. So I just have to solve for N this time. Again, the equation is still the same. You just have to rearrange the equation. Just plug in the values and do the math. Okay, so this is same equation that we saw earlier. We plug in all the numbers. We calculate what is Ln. How do you get rid of natural log? For example, from here, we solve for natural log N0 over N. Now I want to get rid of this Ln. So Ln, this is equal to 0.821. How do you get rid of natural log? Natural log is you raise everything to the power of e. So this raised to the power of e, this raised to the power of small e. E cancels a natural log, and what's left is N0 over N is e to the power 0.821. Your calculator should have a symbol of e raised to power of something. So just plug that into your calculator and solve for this. And now we can solve N is what we need to find, N0 is given, so just rearrange the equation and solve for the final answer. Okay, another thing to remember is, for now we were seeing the number of atoms. What were the number of atoms initially? What is the number of atoms remaining after time t has passed? This N0 and N, you can replace it with whatever quantity you want. For example, instead of number of atoms, we could also do number of mass of the substance. So both total mass of the substance, so initial mass divided by final mass. Nothing has changed. I have just changed N0 to M0, which is, instead of using number of atoms, we're using mass. You can also use this for activity. For example, the rate of reaction. This was the initial activity. This is the final activity. That can also be used instead of N0 over N. Nothing changes, same questions. Only difference is now instead of number of atoms, we could be mass, or we could be talking about activity. For example, like this: calculate the half-life of an isotope if activity of a sample is reduced to 45% of its original activity. So there was an original activity, so we will call that original activity as N0. It is reduced to 45, so now this is my final activity in 1.08 years. So that's my how much time has passed, and question is asking what is t half. So now again the same thing, ln N0 over N, remember these is in parentheses, okay, is equal to ln2 over t half times t. So t is known, N is known. I have to solve for, we have to solve for this t half. Only problem here is we do not know what is this missing quantity, which is what is N0. Because we are talking in percentage, one thing that we know is the maximum percentage that is possible is 100. So this simply means I can assume if the original activity was 100%, how much is it reduced to now? 45%. So your N0 here you can assume is 100. N0 is 100, N is 45, t half is what I need to find, and t is given as 1.08. So again you would just rearrange this equation to solve for t half. So A0 is 100, divided by 45, 1.08. From here we solve for these terms and it comes out to 0.937 years. Last example that kind of compiles everything is cobalt 60 decays with a half-life of this, so this is t half. Calculate the decay constant of the sample. Decay constant means the question is asking what is k. We know that t half is ln2 over k, which means k is ln2 over t half. So we just take ln2, plug it over 5.27 years, and plug it into your calculator, and you get your answer for years. Oh, inverse, whatever number it gives you, 3 sig fig, so that should also be similar. Okay, this is a calculate the fraction that will remain after 15 years. So question is asking how much is the fraction. Okay, so fraction simply means if I take ln N0 over N, so this is the fraction that is original divided by how much is left. So this is how much fraction is left, equals ln2 over t half times t. So if you plug all these values in, because from here we would know what is t half, so take your t half from part A. T is given to you 15 years, so that's my t, and we are just solving for N0 over N. We do not have to solve for one term, it's asking the ratio. Fraction simply means I need the ratio, and this right here is the ratio. So we're just solving for this term right here. Okay, which simply means I raise this to the power of e, so that gets cancelled, this to the power of e. So e to the power of all of this is what's your answer. Next is how long does it take for a sample of this to integrate to 2% of its original amount. So same thing, if I assume my original is 100, it is reduced to 2 ln2 over t half. How much times it takes? So it takes t times. So I'm going to just rearrange it and solve for t from here. And that's my answer. So all the solutions are given to you. You can solve it for your own and then check and confirm your answers.